Okay, so I'm seeing that a lot of people were not able to finish the lab yesterday. So I'm going to go over the lab again today with this video. And so for your asynchronous Wednesday, you can continue working on this lab and hopefully finish it. Um, to start with, we have the simulation here. I'm going to go ahead and open it up in macro scale. And I can see in the image, I have a blue circle on the left that says Q1 and a red on the right that says Q2. Q stands for charge. So I have a charge and a charge. This looks nearly identical to the gravity force lab. So the properties of electrostatic force, which is what we're looking at when we look at charges, is nearly identical to gravitational force, which means the same rules apply. So if I increase the distance apart and make them further away, I reduce the amount of force that they experience from each other. In the same way as if I took two masses and made them further apart, they would experience less gravity force from each other. Now, as far as the mass, when we had masses, if I increased the mass of either or both, the amount of force would increase. And the same thing happens in this case. If I increase the amount of charge, I will increase the amount of force. So note, watch the force up here while I change the charge. So I'm going to increase the charge. Note that the force got bigger. There's another point I'd like to explain in this image. The arrows. The arrows show the direction of the force on the object. So Q2 is being pulled towards Q1. It's being pulled to the left. Q1 is being pulled to the right by Q2. The two little guys show that if they let go, this is the way the object would accelerate. It would go in the direction of that net force. Now, if I were to flip the charge of one of these so that both Q1 and Q2 have the same sign, meaning positive or negative, let's look and see what happens to the arrows. Okay, so what I did is I changed charge 1 instead of -4 to +4. So let's take a look at the arrows now. Now they're pointing away from each other. This indicates that they're no longer attracting, but they're repelling. They're being pushed away from each other. Note the stance of the little dudes is like different. It looks like it's holding it from going to the right. It's like pushing against it instead of pulling it. So what this means is if the little guy wasn't there, this is the direction that the object would accelerate. Notice that when they're both positive, it's a repelling force. So they're being pushed in opposite directions. Now let's look at it with both negative. Oh, same thing again. So we get repelling again, but this time it's just blue to show that both have a negative charge. So whether they're both negative or both positive, they repel each other. And you can see this by the direction that the arrows are going. The arrows are pointing away from each other. When one is negative and one is positive, that's the only time that they're attracted. They're pointing towards each other. Okay, number 1. In the first question, it asks you to think back to the balloon and static electricity lab we did. Now, if I open that simulation and take a look, in this picture, I have 2 balloons and I've charged both of them with the sweater. If I try to get this one to go near that one, it makes it kind of go away. Now, you're not being asked to determine whether or not they'll go apart, but why they're going apart. Now, based on up here, when they're both red or positive, or when they're both blue or negative, they were repelled. The arrows point away from each other. So if the 2 balloons push away from each other, we know that they must have the same charge. Either both positive or both negative? And you don't really have to know which one it is to get this question because we just know that anytime things repel, it's because they have the same type of charge, whether it's negative or positive. The second part of this question says, what might affect how far apart they will be? So this is asking you to think in terms of quantity of charge. When I go back up to the simulation, the amount of force pushing them away from each other changes when I change the charge. So notice that this one's at -4 and this one's at -7. So if I make the charge number one larger, look at the force arrow. See how it's getting bigger? And if I do the same thing for charge 2, watch the arrows. They're getting bigger. Okay, so the more charge you have, the more they push away from each other. So imagine if you are, let's say, on ice skates, or if you're really old school, roller skates or rollerblades, and you stand in front of somebody, and let's say that you only push with your fingers. You're facing each other and you go, whoo, and you push off of each other. You're not going to go very far with that little tiny amount of force. But if you put your hands and you went push, then you're going to go further apart because you've put more force. So think of it kind of like that. So the balloons, if they have a little bit of charge, they're going to have a little bit of force. So they're going to go, whoo. And then if they have a lot of charge, that means that there'll be a lot of force and they'll go further away. So what might affect how far apart they will be? The amount of charge. All right, for number 3, by experiment, determine what makes a force attractive or repulsive. Describe your experiments and observations with some examples. You're provided with a little table to get you started. Describe your experiment and your observations with some examples. Now, at the beginning of the video, we did a few of these already. Anytime we changed a variable and then looked at another variable to see what happened, we did an experiment. So here we're just going to go ahead and document that. Okay, so let's see. When I changed, so what variable did I change? The charge of the left side from negative to positive. Positive. The right side remained positive. Okay. And then what did we see when that happened? Well, when both sides were positive, the forces were repulsive. And before they were attractive. Experiment B, what did you change? I changed both sides to negative. Okay, and then what happened when we did that? The force was repulsive. Okay, So what determines what makes a force attractive or repulsive? Did we prove that with this? I think we did. Here we have that we took the left side charge from negative to positive while the right remained positive. What happened? When both sides were positive, the forces were repulsive. And before, they were attractive. So we've also answered the when is it attractive? When they're opposite. Because remember, the original situation was the left side was negative and the right side was positive. In experiment A, all we did is take the left side negative and make it also positive. So it was originally attractive when they were opposite, but then when we made them the same, it became repulsive. And then just to check it, we did both negative, and they were also found to be repulsive. Number 4, what evidence do you see that Newton's third law applies to electrostatic forces? Just to remind you what Newton's third law is, I just did a quick little Google here. A force is a push or pull that acts on an object and results in its interaction with another object. These two forces are called action-reaction forces and are the subject of Newton's third law of motion. Formally stated, Newton's third law is, for every action, there is an equal and opposite reaction. So if I push on the wall with 50 newtons of force, the wall pushes on me with 50 newtons of force. In this simple drawing here, we see the action force is the person pushing on the boat, and the response is the boat pushing on the person. Here's my wall picture. Here's my wall one that I just said. If I push on the wall with force 1, let's say 50 newtons, then the wall pushes on me with 50 newtons as well. So what do we see here that matches that? Well, we have two forces. We have two objects that have a force on them. The force is the same amount, and it's in opposite directions. So every force has an equal and opposite reaction force. And we can see that happening here. Every time we changed it, no matter what we changed it, the two forces always match, and they're always pointing the opposite direction. So when our charges were the same, they were pointing away from each other, one left, one right. When they were opposite charges, they were pointing towards each other, but still one left and one right. So I would answer that accordingly. What evidence do I see that Newton's third law applies to electrostatic forces? Well, I observe that both forces are equal and opposite, acting on two separate objects. So that would answer number 4. This is going to end part 1. I will continue in the next video, starting with question number 5 and on.